Good evening, everybody. Let's get started. Let me first record on the cloud. All right, we have started recording. So your project one is due almost little less than 2 weeks. So how is it coming up? Let me hear from a couple of you.
So far, so good.
Okay, Mark, good to know. So you're done with that coding part already, or you started?
No, I've started.
Okay, all right. Anyone has any issue with the installation or anything that you want to share? No? Okay, let me then have that. Let me see, where are we instead of, in terms of model sim installation. Let me launch this. Let's take a minute to vote for this one poll. Okay, 24 of 43. Keep it coming. 29 of 43. I'll keep a couple of, maybe another 30 seconds open this poll. We're almost
Hey,
there.
Professor, I can't submit. It won't let me click submit for some reason.
Oh, okay. But are you done with that installation, Avajyoti?
Yes, but I was just having some issues with it though. I've tried a couple of things.
Okay, sure. Yeah, let me know if you need any help. Like you can send me an email or just put it on the discussion. Someone else can help you in your problem. Okay, I think let me end the poll at this point and let's share the result. Let me see. 88% of the class is installed and tried model sim. That's good. Rest of you, please do not procrastinate. You may run into surprising problem. All right. Most of you are on the Windows, 79%, 12% on the Mac. Again, 4 of you, 10% haven't installed yet. Okay, so I think overall, with the statistic, I think as a class, on average, you are in a good shape to go and complete project one. And if you have not started yet, please start. Okay, now let's do some problem tonight. Okay, what I'll do, I will create a breakout room randomly. How many of you are there? 4. Okay, maybe about 12 breakout room. Assign automatically. Okay. And I'm sharing that problem on the class whiteboard, the Jamboard. You can either watch through this Zoom, or you can actually go into that whiteboard. It is being shared, and the link is on the first page of the Canvas course. So find out that link, and you can actually access that in a view only. So let me. So I'll give 2 problems as a group. You guys discuss and come up with a solution in, let's say, 15 minutes. Okay. Let's see. Too small. Okay. Okay, this is not important. Okay, this is 10 to the power 6, 1 million. Okay, so here's a two problem, and I'm opening the room for you, everyone. And let me also open the share screen and chat in case you want to communicate with each other through that. Okay, here it goes. Let's take 15 minutes to solve these two problems as a group, discuss among yourself. And I hope at the end of the day, end of this, someone will present, someone or some, like more than one people will present on this problem, solution of this problem. Okay, let's go. Okay, I'm assigning unassigned Austin and Norway. Okay, let me see. Let me sign here. Let me sign there. Okay.
Hello, Professor.
Hello.
For some reason, my Zoom was having issues. I disconnected and reconnected. Could you put me back into the breakout room?
Yeah, sure. All right, let's wait for a few more seconds for everyone to join in from the breakout room. Yeah, I believe everyone is in. Okay, who is going to explain or give share answer for 1A?
I'll take a shot at it.
Sure.
So we have to find the clock period in nanosecond units. So I remember for one of your slides, you told us that to find this, we can do 1 over the frequency.
Mhm.
So we can do 1 divided by, in the problem it says 1.6 gigahertz.
Mhm.
So that should give us about 0.625 nanoseconds.
Okay, that's correct. Thank you very much.
No problem.
Anyone wants to go with the 1B other than Mark?
Sure, I can do it.
Okay, Matthew. Yes. Okay. All right. Let's see what you have. Can you explain?
You're muted, Matthew.
Okay, sorry, I couldn't figure out how to unmute. So the problem says that it has 40-bit address bus, and that it is a half-word addressable memory, right? So those are like the clues. And 40-bit address bus means we have 2 to the 40 addresses. So that's just converting from bits to the amount of like numbers of them. And then if it's 16 bits per address, then we can find size just by multiplying them. And since 2 to the 40 is so large, you probably should turn the bits into bytes and then just do the unit conversion into gigabyte, which is what the answer they want it in. And so 1 gigabyte is 2 to the 30 bytes. 16 bits is 2 bytes. So if you transfer 2 bytes into the gigabyte unit, and then just multiply everything out, it'll simplify to 2 to the 11, which I believe is 2048 gigabytes.
Exactly. Thank you very much, Matthew. All right. So far so good. How about the 1C? Who wants to go for it? Okay, Yorick, you want to?
I can try.
Okay, all right. Let's see.
If you don't mind that I don't present.
I didn't get your last.
Oh, if you don't mind that I don't present, because I don't have anything on screen.
Oh, okay. Well, yeah, sure. Why don't you explain? Just.
But basically, I was thinking we have 2.5 million operations, right? So the first factor that we need to account for is the fact that 20%, basically 40% of all of the operations are read operations. And let's see, 20% of the, it doesn't actually say, 20% of the write operations are successful, but it doesn't, oh, the rest of them. I think I might have miscalculated, but either way, that doesn't matter.
That's fine. Either way.
I can still do it in a moment. So let's say that the remaining 60% is then write operation. No.
Right.
Okay. So then that means that that basically, let's see, there is, so we have 2.5 million, but on top of that, we have an additional, let's see, we have 20% of 60% of 2.5 million is going to be added to this in addition.
Right.
And then we will multiply this number by 0.265. which is the duration of the clock cycles, and that will be the in nanoseconds. That will be our total measurement of time, and then we will divide that by a million, and then we will get the millisecond duration.
Right, exactly. So the number you got so far, like with that mistake, like what was the number?
Well, with my mistake, the number I got was 1.6, but I see now that it's actually different. So.
Right. Yeah, exactly. But your approach is correct. Your approach is good. So let me share this the whiteboard where I just shared that. So it is should come about 3.3125 milliseconds. So basically what is done, like first is without any delay, without extra cycle consideration, just give the what is the total amount of cycle needed for 2.5 million operation, given that each read or write operation takes 2 clock cycles. So it's basically 5 million cycle it will need. And then extra clock cycle comes from that back-to-back read-write operation, one extra clock cycle, and which is like 20% of the write operation. Now, how many write operations are there? 60% write operations are there. So that's why you see it's like 60%, 20% of the 60% of 2.5 million. So that's why this multiplication goes 0.6 multiplied by 0.2 multiplied by 2.5 million, which comes around 0.3 million. And that means we need total 5.3 million. So we add these and these, total 5.3 million cycle needed. Each cycle is 0.625 nanosecond, which came from 1A. And then we unit convert it, it becomes like 3.3125 millisecond about that. All right, so how about the other one? Anyone other than these three people, Mark, Matthew, and Yorick, other than these three? How about problem number 2? Anyone wants to go with that?
Can you repeat what you just said? I'm sorry.
So other than Matthew, Mark, and Yorick, any other person wants to take a chance on problem 2? No? Okay, how about Mark, Matthew, or Yorick? You three wants to take a shot on problem 2?
Is this from the same problem set?
The problem 2, that's the processor execute instruction, 5-stage instruction execution cycle, runs 1.6 gigahertz clock, connected to memory, which runs on 800 megahertz. How long the processor will take in millisecond unit to execute 5 million instructions. So it's a different problem.
Yeah, I think I can do it.
Okay, sure, Matthew.
I'm having trouble finding like what you just said, the problem, is that I don't have the link to the Jamboard.
Oh, okay. You can go to the Canvas front page, and there you get the link to the.
Okay, but is this the same problem? Is this about the 5-stage instruction cycle?
Right.
Yep.
And it takes and there's 5 million instructions that take.
Let me share. Let me
Okay.
share. Yeah, this is the one.
Oh, okay. Okay, yeah. So I don't have I'm not gonna share a screen. I don't have anything written, but so we're gonna the clock cycle is the same from the last problem. So you can use the 0.625 nanoseconds. there, but we do need to convert that to milliseconds, right?
Okay.
So I believe that nanosecond is 10 to the minus or 10 to the 9, and millisecond is 10 to the 3. So we have to do a subtraction. So we would get like 10 to the, I guess it would be 10 to the -6, right, milliseconds or something like this if we're doing the algebra. But anyway, so you have it in milliseconds now, and it's 0.65 milliseconds. 10 times 0.625 times 10 to the 6 milliseconds, I guess. And then you would use this and times it by the amount of cycles. And then you would also times it by the amount of instructions.
Okay.
So times 5 and then times 5 million. And the 10 to the 6 from the milliseconds in your clock speed or in your time period should be canceling out with the million from the instructions. So it would be 0.65 times 5 and then times 5 again. So you get something like 15.6 milliseconds.
Okay. Anyone else want to counter argue on that logic or agree with this answer?
Isn't it just raw instructions for the 5 million instructions? So the memory clock and the 5-stage instructions are extra information. So you just convert from instructions using the clock speed. And I got something around 3.125 milliseconds.
3.125 milliseconds. Okay. All right. That's there is approach that 5 stages doesn't matter. Okay. How about
Yeah, I agree with him. I'm sorry, I wasn't really like, I think the problem I look at it was different. I didn't see the memory clock.
It also doesn't necessarily say that the CPU interacts with the memory at all.
Okay. Now, let me do one thing. Let me show you. Actually, neither of you are right in that approach. Actually, all these informations are needed and to be considered. First of all, let's see. Do I have this one? So remember, last lecture's discussion we had, the 5-cycle execution of the instruction. There, we saw that each instruction actually needs 5 cycles to get completed. It's instruction fetch, instruction decode, instruction, execution then, and then memory stage, and then write back stage. So uniformly, it will take the 5 cycle. So that means 5 million instruction will take 25 million cycle. However, there is one catch. In that previous discussion, what we talked about is basically your we assume that the memory and the processor are using the same clock. Okay, are using the same clock. So, but in this problem, given in this problem, it says that memory is running in a slower clock, 800 megahertz. You need to ask yourself that whether I can apply the same 5-cycle assumption into this problem. And if not, what needs to be done there? Because in this problem, memory and processor are running in a different clock speed. Okay, so with that note, let's take 5-minute break. So about 8:10, 8:11-ish, we'll be back, and you just keep thinking in that direction. It is very interesting problem.
Hey, does anyone need the Discord link?
Is there a Discord link?
Yeah, so the one that was there from previous year, they're using the same one. I somehow landed in it. If you guys need the invitation, I can send you one.
I think I can use one.
Same.
Okay,
I can use
Yeah,
one
I can
too.
go
Yeah,
with you.
same.
okay, I'll just email it to everyone then.
Thank you.
Yeah.
Thanks.
Yeah. So I sent the links out to as many people as I could. There's way too many people in the class to select every single one. So just email me whoever needs it, and then I'll just copy paste it to you guys.
Or you can just post it in the discussions, I guess.
Oh, but then I don't want the teacher to getting it either.
I think it's already in the discussions, like the introduction. Someone put their Discord link there.
You can also go through the SJSU Discord. It has links to all the other Discords.
Hey,
Oh.
just to note, I'm not interested joining to your Discord. Okay?
Oh,
I guarantee you.
okay, that's fine. That's fair.
We could use your help in there.
Hey, let's get back to our interesting discussion. So let's see. Let in this problem, both the memory and the microprocessor, they are running in a different speed, right? And you see that this is like this is a 2x speed compared to this guy, right? 2x of this 800 megahertz multiplied by 2 is 1.6 gigahertz. So that means if you put in a timeline the clock for the microprocessor, if this is something like these cycles are going on, then, and if you put the clock for the memory, it will be something like this. Let's say they are on here, and then it will be like a double. So it's basically takes a double time than the clock of the microprocessor. That means your stages, which involves the memory access, means these, which is instruction fetch, and memory, which is the memory stage, mem and instruction fetch. It needs to wait for memory to respond. Okay, so we attach a slower memory in this system. So what we need to do architecturally in this processor, when we design it, we need to accommodate for that slowness of the memory. That means what we need to do, we need to split the instruction fetch and memory into two signals, like this, like maybe it is instruction fetch cycle 1, instruction fetch cycle 2. It is just to accommodate the slowness of the memory. And similarly, another cycle for the mem1 and mem2. Now you see this whole system become a 7 cycle. So your answer is basically 7 cycle per instruction, 5 million of instruction multiplied by what is the clock speed was? Clock speed was 1.6 gigahertz with respect to our microprocessor. So this comes down to, it's the same thing at the previous problems, 0.625 nanosecond. So if you do that math, it becomes like 3.3125 millisecond. So this is how you need to approach this problem. Question?
Professor, could you go back to the whiteboard?
Yeah, sure. Yep. Mark, you can access it like through the Google Jamboard.
Oh, okay. Thank you.
It is there in the canvas. I think that would be better so that you can better observe it. I think
right.
It might be a little distorted. But anyway, so that is how you...
Professor, I have a question.
Yes, Jerry.
What if the processor or the CPU is not exactly 2 times this clock speed of the memory? What happens to the extra instructions or extra cycles?
So basically, in that case, we need to somewhat make it a common ground between these. This is more like an LCM calculation. Okay, so we need to put enough cycle in the microprocessor so that it covers up the memory slowness. So you go with the ceiling of that multiplication value. Like let's say this was like 2.3 or 2.5. So you go with the 3 cycle there, and that is one way. And other way is that like we can go with the asynchronous approach. Means that is a little bit difficult, by the way, to implement as well. But let's say we want to place a done signal between them, like instead of just assume it will be done in a 2 cycle or 3 cycle. So it will basically will become like a done signal from the memory. So, and the instruction and the state will wait on that. How is it can be, it can be done. It is something like this. Let me go to the next page. So in the state machine, so I think many of you have gone through that finite state automata subject, maybe, or maybe not, doesn't matter. So instruction fetch, then my state diagram would be something like this. If it is not done, so this done is being sampled at the clock edges, positive clock edges of the processor clock. Until it is low, it will just keep on staying there, and then it will move to the next next phases. EXE, and then similarly we need to do the same thing at the memory. Not done, and then go to the write back. So here we introduced a new signal between the processor and the memory for an asynchronous handshake. Okay, so that way we can do that, and then your calculation, time consumption calculation would be similar.
Okay, thank you, Professor.
That's a good question, Jerry. Thank you. Keep it coming. All right, now let's do two more problems, maybe individual, from the number system. Let's just practice our number system study. So two problems, let me give you like this. Okay, and where's the time? 8:20. Take 5 minutes. 5 minutes to solve this problem individually. No group work now. It is individual problem. Take your time, 5 minutes to convert these numbers. Okay.
We're assuming that this number system is base 6.
That you need to decide.
Okay.
The problem.
Okay.
There's actually 7. The one's cut off.
Yeah, exactly. You are right. It is a base 7 because there are 7 symbols. Okay, let's see. Anyone wants to go for number 2 first? Okay, let's see. How about 1A? Anyone?
I can do it.
Okay, Nigwin, please.
So, give me one second. Let me share the screen.
Do you want
Oh,
to?
Yes, please. Can I share the screen?
Yeah, sure. Right.
All right. All right. So, we got mi re re do, which is converted to 2, 1, 1, and 0. And then do is at the 0th place, so it's going to be, because this is base 7, do at 0th place, so it's going to be 7 to the power of 0. Re going to be 7 to the power of 1, and so on. So when we do that and add up, we got 742.
Okay, that's great. That's great. Yes, that's the answer of that one. And I see you just started on that next problem.
Yeah.
That's good. You actually having, yeah, it's a good, right approach. Anyone? I just wonder, anyone else has completed that one? Okay, then I can go just to show you. I believe you know that already, just to be everyone on the same page. Let's do that. So this one would be, let me see if I can turn on my other computer. Hey. What happened to this one? Okay, yeah, I think so. Yeah. So next one would be you keep on dividing that number. So we start with 1045673, 1045673, and keep on dividing by the base of this number system, which is 7, and calculate, note down this quotient and remainder for this division operation. So this first division will give you 149381, 149381 as a quotient, and as a remainder it will be 6. And 6 is this t. So this is t, and then we take this previous quotient and keep dividing it, 149381 division 7, which will give you 21340 with remainder 1, which is re. 1 is re, and then 21340 divided by 7, which will give you 3048, remainder 4, which is 4 is so, symbol so, 3048 division 7, which will give you 435 as a quotient, and remainder as 3, which is symbol fa, then 435 divided by 7, which will give you 62, remainder as 1, which is re, and then 62 by 7, quotient 8, remainder is 6, which is t, then 8 by 7, quotient 1, remainder 1, it is re, and then 1 by 7, quotient 0, remainder 1, it is raised. So we keep on doing this division till we reach a quotient 0, and then we write the representation in that new system as from down to up in that sequence. So it is re, re, ti, re, fa, so, re, ti. Okay. Now, how about the second one? Anyone is thought of anything to do
Oh
about
yeah.
this?
Uh-huh.
Yes, Ahmed.
So what I did was I made the decimal representation of 12, which was 1100. And then for a two's complement, you're supposed to switch the numbers, and then you're supposed to add 1. So it becomes 0011 plus 1. So you have to carry the 1, and it becomes 0100.
So this one is two's complement is 110110. So it becomes like what?
The final answer, I believe it's 0100.
0100.
Mhm.
Okay, anyone wants to agree,
I think-
disagree?
I think I have to disagree.
Okay, Matthew, what's your reason?
So it's 4's bit, right? So 4's bit has a range. Is this out of range or?
I think you are in the right direction, Matthew. So Ahmed, we need to first see if we can even represent these 12 in 2's complement value or not. What you represented as a 2's complement is the value 1, 2, 4, value 4. It's not 12. Why? Because the range of this number is 4-bit 2's complement is from -8 to 7. So you cannot represent 12 with 4-bit 2's complement representation. It is not possible.
Oh,
In
okay.
general, if you have n number of bit, the range is 2 to the power n minus 1. This is okay. Where is it? Minus of that. This is a negative range, negative lowest number that you can represent. And then your upper range would be 2 to the power n minus 1 minus 1. So if you stick in n as a 4 here, you will get -8 to 7. So you cannot represent the value 12 in a 4-bit.
Oh, okay, thanks.
Okay, wonderful. So, all right. Now, how much? Okay, we have some time.
So would it be
yeah, Matthew? Yeah.
Oh, would it be represented as -4? Like, does it circle back?
This one?
Like 12 in 4's bit, or is it not possible to represent it in 4-bit?
-4?
Yeah, is it possible to represent 12 in 4-bit 2's complement?
No, it is
Like, would
not.
it circle back? Or okay.
No, it is not. It is not. You need 5-bit for in 2's complement format. You need at least 5-bit for representing a value 12.
Okay, thanks.
So it sounds like you're using the flip bit method, right? And
Yeah.
in that method, if you ever have a positive decimal value, you actually just directly write the bit pattern as positive. It's the same. Positive numbers are the same in 2's complement as they are in normal, just binary representation.
Oh, okay.
So you don't have to do the flip.
Thank you for bringing up this point. Yeah.
You don't have to flip it.
So only thing is that you make sure that in the positive representation, the MSB is always 0. If it is a 1, it starts with a 1, it's a negative number, always.
Yeah.
All right. So anyone has any other question from our theoretical discussion, last night topics, these topics, today's topics, anything? Okay, so let's look at what is upcoming for the next day, what you need to study about. Okay, you need to study about this thing. Let me see, course module, share. Okay, so we are in module 2 and next is lecture 5. So this is like this is more important. Okay, like Boolean algebra 1 was important too, but it was more like a refresher of your math 42, your logic algebra study, etc. This one, on the other hand, is needed for digital circuit design, this concept and application of this part. So please pay more attention onto this one. It has two parts. One is discussing the standard form. What is a standard form, where it is applied and stuff like that. And from there, it goes into an optimization technique called Cardinal Map or K-map technique to reduce the Boolean algebraic expression. So these are the two topics. It has a pointer to your reference textbook. You can go there and for more information if you need. And then it goes about standard form discussion about sum of product of sum. Please make sure you understand what is the definition, how they are written, and so on and so forth. And we discuss about like POS and SOP. These two representation are basically equivalent representation of the same Boolean expression, and we'll stick to the SOP in the rest of the semester mostly. Okay, so and then we talked about from a given truth table how we can write down the SOP. Also, given a truth table, how we can write down a POS. That's a very important concept. You need to be very clear of that. And then we talked a relation between the SOP and POS to prove that, okay, any given expression, they are equivalent. Like if you have no POS, you know corresponding SOP and vice versa. So we can just focus on one of the form for rest of the semester. So this is an interesting study there. Then we move to the Cardinal Map Technique, which is you need to practice a lot. Okay, this technique, use that technique to like reduce down different given Boolean expression and formulas. So we talked about that, different structures, 1, 2 variable, 3 variable, 4 variable K-map structures. And then we talked about the rules of grouping them and deriving the prime implicant, essential prime implicant, and different scenarios where you need to decide which one you want to pick up if there is a multiple choice to group into a prime implicant, which one you want to make an essential prime implicant, and those kind of discussion and concept you need to be very clear of. So make sure you went through that one. And then we talked about some rules of the map manipulation and definition, what is an implicant, prime implicant, and what is the essential prime implicant. And then we talked about the map manipulations. And then we talked about another interesting concept of use of don't care terms, how we can use it to reduce our Boolean expression further. But here, what you need to be very clear of, what is a don't care term, why a don't care term can appear in a Boolean algebraic expression. It does not appear in a math world, by the way. It is purely a digital world concept that there is something called a don't care term. It's neither zero logic or one logic. It's saying that this logic, I really don't care about that combination of logic. So that's the concept. And later we'll see, I think that in the next lecture videos, you'll see where this don't care terms comes from in digital world. Okay. So please make sure you understand this concept as well. We have like 5 parts of videos. Please go through them. and note down your questions in the module 2 discussion page. All right. Any question or comments? No? Okay. All right. Then let's close for tonight.
Professor, quick question.
Yes, Mark.
So before we start module 3 on Tuesday, do you expect us to be done with all of module 2 videos?
Module 2, so come again with your questions.
Yeah, so before we start module 3 next week, do you expect us to have already finished all the module 2 videos?
Yes.
Okay.
That's the expectation is.
Got it. Okay, thank you.
Okay, all right. Good night, everybody, and have a nice weekend. See you on next week.